This video is brought to you by Group 2.
本節目由以下单位赞助播出。この番組はご覧のスポンサーの提供でお送りします。
It's such a great pity that we couldn't see much more about your research in that season.
It's harsh to say, but I still have to inform you. You know what is going to happen if your performance is below satisfactory.
Alright, take your time, Mr. Chicken. Hello everyone, I'm Joyce from Group 2. Let's take a look at today's briefing schedule. First, we are going to do a simple introduction for the main character of our circuit, Multivibrator. Then, we will explain why we choose it as our topic research personally and theoretically. Third, we will analyze the circuit and see how we derive the math part. Next, we will show you how we use Python to solve differentiation equation and do simulation. Last but not least, final realization. We will present our circuit in real life and analyze it with theoretical value to prove that we did the right choice. Before we head into our design, let us see what is a digital clock signal generator. Take a look at the following illustration. As you can see, we have time for the x-axis, then we have voltage for the y-axis. The clock itself is built by the square wave, which triggers rises and falls periodically. How to generate such wave? Here's our final circuit designed to realize the square wave, and it is called Multivibrator. The triangle in the middle is called operational amplifier. In short, we call it OPAMP. Now, I'm going to show you how it works in the circuit. So, what can we do with an operational amplifier? Operational amplifier is really useful when it comes to basic math operation. It has two inputs. One is the positive one, and the other is the negative one. Just like its name, it amplifies this input voltage. We can imagine the triangle is a black box since there is quite a lot of ICs in this little triangle. The two inputs makes it a great comparator, and comparator is widely used when we need to generate an analog signal into a digital signal. Here's what the black box looks like. The operational amplifier we use for our circuit is LM741. The black box looks like a bit complicated, isn't it? Here's what we need to know after simplification. An operational amplifier has two voltage inputs, one negative input and one positive input. To enable the amplifier function, we need to supply power to it. So we have the positive voltage supply and negative voltage supply, which need to connect to power supply respectively. Finally, we have output on the right-hand side. A multivibrator has two states, stable and non-stable. There are three types of multivibrators: a stable multivibrator, monostable multivibrator, and bistable multivibrator. For the unstable multivibrator, the circuit is not stable in either state. For the monostable multivibrator, we have one stable state while the other state is unstable. A trigger pulse causes the circuit to enter the unstable state. After entering the unstable state, the circuit will return to the stable state after the set time. For the bistable multivibrator, the circuit is stable in either state. We want to use ordinary differentiation equation to solve the problem. On the other hand, we're mostly students from EE program. This is why we choose it as our topic, since we would like to combine the power of new knowledge and what we've learned in other classes. Even though we have experiment class, it is still really challenging for us. The second thing that motivates us is that circuit is relatively more stable if we compare it with other systems that mainly relies on gravity. We would like to make it as precise as possible because the topic is all about time.
In order to construct our clock circuit, the following are some basic mathematical laws implemented. First of all, the Ohm's law. In all the electronic circuits,
voltage is always the product of current and resistance. This is significant for the differential equations as the definition of current is the change in number of charges over a certain amount of time. In addition, the Kirchhoff's current law and the voltage divider are utilized for mathematical analysis. A capacitor is a circuit element with the physical structure as shown. The characteristic of it can be described as the total charge is the product of capacitance and voltage. Its function is to store the voltage when the signal voltage increases. This is called charging. On the other hand, it can release voltage into the circuit system when the signal voltage decreases. This is called discharging. A comparator can create two output voltage states by comparing the signal voltage and the threshold voltage. When the signal voltage is greater than the threshold voltage, the output is positive VO, and when the signal voltage is less than the threshold voltage, the output is negative VO. Schmidt trigger is a comparator with positive feedback. An ideal op-amp would have no current flowing into both input terminals. At the non-inverting input terminal, the voltage can be found using the KCL. I equals to V out minus V plus over R1 equals to V plus minus 0 over R2. And the voltage at the non-inverting input terminal will be equal to R2 over R1 plus R2 times V out. For better representation, we define beta as R2 over R1 plus R2. To analyze the inverting input terminal, simplify and redraw the circuit as shown. So Vout is switched between negative VO and positive VO. In the first case, Vout will switch from negative VO to positive VO. Then the non-inverting input terminal will equal to the threshold voltage, which is beta VO. As previously mentioned, the inverting input terminal at t equals 0 is thus negative beta VO. In the second case, Vout will switch from positive VO to negative VO, and the non-inverting input terminal will equal to negative beta VO, while the non-inverting input terminal at t equals to 0 is beta VO. Here is the derivation of voltage at the inverting input terminal when the capacitor is charging. These are what we mentioned. By Kirchhoff's current law, I equals to Vout minus V inverting over RF, which is equal to C times dV over dt. And here Vc is represented by V inverting. So after integration, we'll get V inverting equals to VO plus Ke to the negative t over RFC. The initial condition is that V inverting is equal to negative beta VO. By implementing this initial condition into the derived equation, we obtain V inverting equals to VO minus 1 plus beta times VO times e to the negative t over RFC. In order to obtain the amount of time that this state holds, we could assume that t equals to t1, and V inverting is charged to the threshold voltage beta VO. Then we could know that t1 is equal to RFC times natural log of 1 plus beta over 1 minus beta. This mathematical result indicates that the output voltage will be kept high for t1, and the output is inverted as it reaches the threshold voltage, and so is V non-inverting, which causes the capacitor to discharge. Since the equations for both cases of charging and discharging are similar, but with the opposite sign, the derivation will be omitted here. According to the calculations, we can obtain the amount of time that the capacitor is charging, as well as the time it is discharging. This is why the duty cycle of this circuit system is 50%. Our period t is equal to the sum of t1 and t2, which is 2 times r times c times natural log of 1 plus beta over 1 minus beta. We get to choose that beta is equal to e minus 1 over e plus 1, which is around 0.462, in order to obtain natural log of 1 plus beta over 1 minus beta to become 1. This way we get t, the period is equal to 2 times rf times c. This circuit switches between the discharge and charge cases of capacitor, and it forms a cycle such that the output voltage is continuous square waveform. Finally, we reach our mathematical models that we used in Python program, and these are for when natural log of 1 plus beta over 1 minus beta is equal to 1, assuming that V out is equal to negative VO and V inverting is equal to beta VO at t equals to 0.
Hi, I'm Eva. After doing theoretical analysis, we're going to simulate them. To simulate, we use LT Spice to practice. Then we use some Python packages like NumPy, Matplotlib, and SymP to do the simulation. Let's start with what we accomplished in the midterm. First, we use LT-Spice to draw and simulate our circuit. The reason why we use LT-Spice for the very first step of simulation is that it's closer to reality, so we can check the visibility of our circuit. It also can keep track of various data and information. Furthermore, it's more convenient to choose the right voltage source, preventing the bad design which definitely would break the circuit. This circuit is the core of our project. We use it to simulate the output voltage, the inverting input voltage, and the non-inverting input voltage. The following graph is from the result of the LT-Spice simulation. We use a Python package simply called LT-Spice to process circuit data which we export from LT-Spice, and try to make an animation to show the variation of the data dynamically. Unfortunately, the sample rate of LT-Spice is not a constant. Thus, we resample the data, trying to make the time interval between frames fixed, but it causes the animation not being accurate enough. So we try to build our own model. We use SIMP to solve the charging and discharging differential equation of the RC circuit. Then, we compare it with our math model derived in the previous session. After that, we determine that our model is correct. We start to build the model on Python. We assume the output voltage, or simply Vout, is low, and the capacitor discharged from beta V 0 in the first half cycle. So Vout is equal to negative Vo in the first half cycle, and it is equal to positive Vo in the second half cycle. The same goes for the non-inverting input, but it is multiplied by a chosen constant, beta. For the inverting input, it discharges from beta Vo in the first half cycle, and it charges from negative beta Vo in the second half cycle. The charging and discharging functions are based on the math model. Be aware of the second half cycle. The time origin for charging is half of the period, so we need to fix it in the function. First, we plot off data and fill the animation again. Because we can decide the sample rate of the Python model, the new animation is smoother than the old one.
This is a light-emitting diode, or simply LED. Whenever it is conducted, it will release the energy in the form of light. This is a simplified model of an LED. As you can see, an LED will be turned on when the voltage across it goes beyond a certain voltage value. Thus, we use it as the negative voltage filter. We can also observe the output of the multivibrator as long as the period is long enough. This is a variable resistor. We use it to adjust the feedback resistance of the OPAMP. This is a 7-segment LED display. With a decoder, we can transform a 4-bit binary number to decimals and display. Due to the persistence of vision, if the light flickers with a frequency that is larger than 15 Hz, it will look completely steady. But humans' hearing range is between 20 to 20,000 Hz. It is completely separated. So, if we want to see and hear the signal at the same time, we need to generate a higher frequency first. Then we use a frequency divider to generate a new signal that has a lower frequency. Both the high and the low frequencies are linear dependent. Here is a brief intro of the design. We implemented 2 LEDs to observe the voltage signals visually. There is an LED flickering at a high frequency and another at a low frequency. In reality, it works exactly as expected, but it doesn't act like that in the demo video due to the sampling rate. The third one is a 7-segment display counting from 0 to 9 repeatedly at a low frequency. To hear the voltage signals, we have 2 modes. The first mode is just playing the square waves generated by the multivibrator. Since the pitch is decided by the frequency, it can be used as an instrument. The second mode acts like an electrical metronome. We combine the high and the low frequencies such that the sound is theoretically discontinuous. We fix the capacitance of the multivibrator for simpler measurement. Here is the block diagram of the entire system. The multivibrator generates a high-frequency square wave, and through the LED, we filtered the voltage at the negative region to make it in the recommended working conditions of digital ICs. Then we generated a low-frequency signal for visual displays. The high-frequency signal also connected to a switch along with the speaker system. Last but not least, we use AND gates to combine the two signals. They are also connected to another switch so that we can switch between the two modes easily. This is a detailed circuit for implementation. To have a wide adjusting range and be capable of fine-tuning, we connected 3 different variable resistors in series as the feedback resistor. Here's the list of components excluding the breadboard and wires. We adjust the feedback resistance by turning the 3 variable resistors at the top of the system. This is the 7-segment display. This is a switch for turning on and changing the audio mode. This is the speaker. This is a resistor for adjusting the volume of the speaker. We use a multimeter to measure the total resistance of feedback resistor. Then we use an oscilloscope to observe the waveform and measure the desired information such as frequency. After collecting the data, we use Python to analyze it. The gray dots are the data. The blue lines represent the regression line. The yellow lines shows the ideal value. Even though there are some errors between the measured and the ideal values, the difference is not significant. Thus, we can simply multiply a correction term to obtain a more accurate model. The error rates are mostly between 15 and 20%. One possible solution to these error rates is to choose another beta to cancel out the correction term.